this topic. I was discussing about the step-by-step analysis or step-by-step procedure. Let me share the screen again. It's not opening. All right. I was discussing about the serial correlation. Now, what causes autocorrelation or serial correlation? If you are having missing variables in your data, like I have discussed right now in my previous part about the variable omission. So if some important variables are omitted in from your data, there is a chance of autocorrelation or serial correlation in case of time series or panel data. So error term may include all the variable not included in the regression equation. So in case of error term, there there might be there might be some variable that you have not included in your model, so they may contain in your error term. So in that case, there is a high chance of autocorrelation or serial correlation. So change in any of the observed, unobserved variable in one time period may impact the error in different time period. So error may follow the pattern trend of unobserved variable. So there is a high chance if your important variables are missing from your model, there is a high chance that there might be some serial correlation in your data. So y depends on x1, x2, x3, and you have not included some of the variable, like you have not included x2 in the model. So sales depends on seasonal changes and it is not included in your model. So there is a high chance that serial correlation may uh, apply in your data. Then there may be a chance of inertia or sluggishness. Speed of change in variable depends on time, business cycle like GDP, prices, etc. So there may be a chance if a sudden or speedily change arise in some variable, like speed of price change may depend on how far it is from equilibrium in the price. This is a common phenomenon in time series data. So whenever you have data related to GDP, related to price, because we may record sudden changes in prices, we may record sudden changes in GDP. In that case, there is a chance of serial correlation or multicollinearity issue in our data. Then you may have incorrect functional form. uh, that is basically the linearity of the data. So if linearity of the data is violated from your model, then there is a high chance of autocorrelation in your data. So autocorrelation may exist if linear model are specified and when non-linear are required. So linear, variable, or simple models are used when long form is needed. This is called model specification error. So we can check the model specification through link test that we have previously done model specification. So this using this test we can confirm whether there is a model specification in our data or not. So if there is a variable omission and there is a model specification, there is a high chance that our data may contain the autocorrelation or serial correlation problem. Then there is a pure economics function which is known as cobweb phenomena. It is a reaction with the lag. So when the dependent variable acts with a lag, we may observe autocorrelation. So whenever you are using the lag model, like you are taking the dependent variable as a lag in your model, and you use it as a independent lag variable in your model, then there is a chance of autocorrelation or serial correlation in your data. Similarly, lag relationship. Uh, One reason may be that the dependent variable may depend on its previous value. Like in case of GMM model, it is assumed that your dependent variable may be dependent upon the previous values. Then it is a chance of high multicollinearity. Ratchet effect. What does it mean by? The tendency of people to be influenced by the previous high, low, or best level of the variable may cause the ratchet effect to exist. Another example is consumption. Consumption changes quickly upward when income goes up, but does not come down easily if income declines over or underestimation. So, whenever your income increases, you try to increase your consumption expenses, but whenever your income declines, it is very difficult for you to decline your expenses too. That is known as ratchet effect. So in case of ratchet effect, it is a high chance of multicollinearity or serial correlation. Sometimes you manipulate your data manipulation in the following ways may cause problem. What are the ways? You apply averaging or smoothing in your data set. You convert quarterly data to annual data. You convert monthly data to quarterly data. You are finding midpoints when faced with ranges. You sometimes we need to do the above because of measurement error. Monthly data by byproduct is autocorrelation. So whenever you convert your frequency of the data into different types of frequency, from monthly to quarterly, from quarterly to annually, or from annually to quarterly, and from quarterly to monthly. This type of data manipulation would result in uh, basically serial correlation or autocorrelation. And the eighth one is systematic measurement error. Sometimes our variable may have not correctly measured. It is known as measurement error. In one time period may be carried forward. Measurement error in inventories, measurement error in stock of capital, measurement error in asset value, all can cause problem of autocorrelation. This is why time series has a noisy proxy. So always remember that if there is a measurement error in your model, there is a high chance that the autocorrelation or serial correlation may arise. Then you may have variable behavior, electricity consumption at different hours of the day. Similar temperature pattern may cause pattern in error. Sometimes, especially in the hot summer season, people used to people try to use air conditioner in their room in different hours. So electricity consumption may rise in some particular time period. That may also cause the change in the behavior of some particular variable. So they may cause the autocorrelation or serial correlation. Then there is a special category of autocorrelation, that is spatial autocorrelation. What does it mean? This is a special cause of autocorrelation in cross-sectional data. So if you are using cross-sectional data, you may face spatial autocorrelation. Everything is related to everything else, but near things are more related than distance things. This is basically uh, a scenario in cross-sectional data. So the first law of geography by Waldo Tobler is that everything is related to everything else, but near things are more related to than distance things. This is the law of geography by Waldo Tobler. So spatial autocorrelation is a correlation of a variable with itself through space. It is due to a systematic pattern of the spatial distribution of the variable. So sometimes the nearby areas are more like positive autocorrelation values in the sample do not remain independent. The occurrence of the one event in an area makes it more likely in the other areas. So areas with higher concentration of events will have more impact on results. So this is spatial autocorrelation. We don't need to worry about it because we are not going to use cross-sectional data. Mostly we are going to use the time series or panel data. So this spatial autocorrelation applies in only the cross-sectional data. So here is an example. In Karachi, due to high crime rate, more police and rangers are deployed. So there is a high chance of autocorrelation regarding the deployment of police and ranger with the high crime rate. So if you collect data for the crime rates and also the deployment of police and rangers, it will create autocorrelation. Due to Karachi operation, the crime rate decreases in every decreases in Karachi. So due to increase in operation, the crime rate decreases. This also create the autocorrelation. The crime rate in nearby cities will increase, although they do not decrease police. So this is another thing. So what will happen if autocorrelation or serial correlation exists in your model or in your data? What will happen to your results, whether they are validated or whether they are not validated? So consequence are estimators remain unbiased and consistent. Estimators are not more efficient. It means you are not going to interpret your estimators or beta's value if there is a autocorrelation or serial correlation in your data. Standard error of estimate or variance of the error is likely to be underestimated, resulting in overestimated R square. R square may be overestimated. They may be showing a high value of R square in the presence of autocorrelation. Variance of estimators are biased. It means you are going to see a very high value of variances. Forecasts are unbiased but inefficient. You are going to have some forecast, but they are not reliable forecast. In case of positive autocorrelation, standard error of coefficient are too small. It means it will decrease the standard error. If there is a positive autocorrelation, it will decrease the value of your standard error, uh, due to which your t value will increase. In case of negative autocorrelation, your standard error will be large, and in that case, your t values will be small. So you need to understand whether you are facing a positive autocorrelation or a negative autocorrelation. So with the help of Durbin-Watson test, we will let us this test will let us know whether there is positive autocorrelation or negative autocorrelation. In case of positive autocorrelation, t value is high, and in case of negative autocorrelation, our t value will be lower than actual. So we need to know how much the value is. So this test first order autocorrelation with exogenous regressor. It is not good when repressor are not exogenous. It is not good when the model contains lag dependent variable. Always remember that if you are using lag dependent variable in your model, then you don't need to use Durbin-Watson statistics. So always try to use this test when you are not using the lag dependent variable. So what is the procedure of running the Durbin-Watson statistic? First, you need to run the regression, and then you need to run this. So let us use some time series data here. Let me clear this data set. So you need to write the clear command. It will clean up the data from your data set from data editor 2. So you need to open some time series data. I go to the file, I go to open. I will also share this data set. For example, my time series data. I can use it. I can also use the PSX data, or I can use the time series data. So for example, I am going to use the PSX data or my time series data. Let use my time series data. I will share this data set. We may have, if we see here, we may have a time dimension. We may have a number of variable here. So let me check this command first, then I will share this data set. First, we need to rec with robust command. So let me rec the data. Reg. Let's suppose oil price is dependent variable and education and health. These are independent variables. So oil price is dependent and education and health are independent. Then comma and row. So it will run the command and you will see here the model is fit. The R square is 81%, which is a good R square, and you can see the coefficient are significant. But we need to check whether there is a autocorrelation in this data or not. So dwstat is basically the command which we are going to use here. So dwstat, click enter. Time variable not set. Use ts set variable name. All right. So ts set and time dimension variable is time. Click enter. Always remember, when you are going to use Durbin-Watson statistic, you should have a time series variable. And in order to declare the time series, you need to write TS set and along with this, the time dimension. If you are using year, put the time dimension as a year here. If you are using month, you need to put here the month. So whatever the time dimension in your data, you need to put it here. Then you can run your regression command again like this, and then you need to run Durbin-Watson statistic like this. Now it is run and you have seen some value, that is 0.381211. This is the value of Durbin-Watson statistic. Now I need to interpret this value. What does it mean? D lies between 0 and 4. This is the value of D. The value you are seeing here is the D value, which is Durbin-Watson statistic or D statistic. This is D value. So this value should lie between 0 and 4. So what does it mean? As D is closer to 2, the chances of AC decreases. If D is less than 2, this may indicate positive AC. All right. If D is greater than 2, this may indicate negative AC. So in our case, our D is less than 2 and it is closer to 0. It is less than 2 and it is closer to 0. So here is more interpretation. The Durbin-Watson statistic will always have a value ranging between 0 and 4. A value of exact 2 indicate there is no autocorrelation detected in the sample. Values from 0 to less than 2, our value is basically close to 0 and less than 2 points to positive autocorrelation, and the value from 2 to 4 mean negative autocorrelation. So basically this applies in our case because our value is less than 2 and close to 0, and you can see here this is the value 0.38. It is less than 2 and close to 0. So we can say that there is an autocorrelation in our data, and it is positive autocorrelation. So what does it implies? It implies uh, when we have a positive autocorrelation, it means our standard error are too small, resulting in overestimation of t statistics. So in this case, we can interpret that the t values here are overestimated. It means these are not correct t values. These are overestimated t values because our standard error are underestimated. So this is the interpretation. In this case, there is a autocorrelation. There is a positive autocorrelation in this data. Our standard error are underestimated, and our t values are overestimated. So what further we can do with this autocorrelation? There is another test which is known as Bruce-Godfrey LM test. Bruce-Godfrey LM test has an advantage over the classical Durbin-Watson D test. This Durbin-Watson test relies upon the assumption that the distribution of residual is normal. So if your data is normal, then you should use Bruce Godfrey test. But if your data is not normal, then you should choose to use Durbin Watson t test. So we need to confirm whether our data is linear uh, or not. So in order to do that, we need to use predict e comma residue. This command creates the e. Then we need to correct we need to consider a regression command like this, and after this we can use the normality command in order to check whether our data is normal or not. We have used, yes, these are the tests, like for example s will e test in order to check the normality of this data. Our data is not normal because p-value is less than 5%. So we cannot use the command that I was stating here, Bruce Pagan Godfrey LM test. So this test is used uh, when your residuals are normal. So always remember this. If your residual are normal, you can use the Bruce Godfrey LM test. But if your residuals are not normal, then the result of Durbin Watson test is fine. So what is the procedure of using this test? You can use the test using this procedure, and it will let you know if p-value is less than 5%, serial correlation is there. If p-value is greater than 5%, serial correlation is not there. So always remember, if your residuals are normal, you can use this test. Otherwise, Durbin-Watson statistic is okay. So what to do if serial correlation is found in your analysis? This is the last thing after which we will complete our session. So to correct the autocorrelation problem, use the praise command instead of regression. So what you need to do, you need to use praise commands and correction command here. So this is the command that you need to use if serial correlation is found. In our case, serial correlation is found with positive autocorrelation. So we just need to replace our DV and IV from here. So use your DV and IV, copy from here and put it here in place of this. And we have put it trace in the starting part and correction in the last part in order to rectify the issue of autocorrelation. So it has generated the result. You can see here the R square has decreased. Previously, the R square was very high. It was 81%. Now the R square is only 30%. And you can also see the T values. Previously, the T values were high. The T value for education was 12.18%. And I have told you that due to positive autocorrelation, the standard deviation may be underestimated and your T values may be overestimated. But after correction, your T values are rectified. Now your education variable is weakly impacting your dependent variable, and your health variable is impacting significantly impacting your dependent variable. So we can conclude we can conclude our result with these corrected findings. So whenever you are facing a serial correlation in your time series data, especially positive serial correlation, this command will rectify your regression results. So now it is completed. Our process is completed. Our basically whatever we have discussed today are assumptions are completed today. So we have completed our assumption. In our next session, I will let you know how to transform your data if you find some linearity issue, if you find outliers, if you find multicollinearity, autocorrelation, residues, or other issues, if you have variable omission and so on. There is a technique which is called variable transformation. I will let you know in the next session that we will conduct on Monday. So if you have any question, you may ask for today's session. We have completed our assumptions. So in the next session on Monday, we will cover some advanced technique like transformation technique for correcting our data. So Adnan, Afzal, and Wakar, do you have any question for today's session, or should we conclude it? Please let me know, Adnan, Afzal, and Wakar. There is a message. Thank you, dear. All okay. All right. Uh, so let's conclude our session. We will meet on Monday with the remaining part, with what we could not discuss today. That is the transformation technique. We will discuss on Monday with the same time. Thank you, everyone. Stay blessed and stay safe. Thank you.